Welcome to the last segment of the lesson on Julia core programming. In this lesson, I put several different things, small or medium size issues. So this is why I gave the name of further topics, because these are pretty heterogeneous. So we start by running the stuff to set up the environment as normal, and we start with the macro programming issue. So metaprogramming and macro. As I said in the kickoff meeting, metaprogramming and the possibility to write macros in Julia is one of the most nice aspects of this language. But before we going to see more in details what does it mean and what you can do with metaprogramming, let's just to remember as a little bit what happens when we run a command, a statement in Julia, which are the passages, more or less. The first things, you have some text code either on the file or you as the command that you type on the terminal, and the first things that Julia has to do is to parse this text and transform this in code expressions, and it does that by composing by hierarchically something called the abstract syntax tree that we will see. And it is these three contain the expressions of that make the code, the commands, and it is at this level that syntax error are caught. For example, if you forget to put an end at the end of a block, then these remain in memory as expression. We know object yet instantiated, so there are the variables, but the variables are still empty, not even with nothing. There is just the variables and the idea of the code. And at the first time that the program call a function that is in the abstract syntax tree, Julia will compile it just in time using the LLVM compiler in object code, and at this point it will execute this object code. At next time that the function is called with the same type of parameters, Julia will reuse the code that has been compiled, and so this compilation happens only the first time that the function is called. One of the key aspects of metaprogramming is that it allows to write macros. But what in turns are macros? Well, in other languages, macro often refer to some step that happens before the compilation. For example, in C or C++, this is done by a so-called preprocessor, and it refers to the possibility to really manage the textual representation of the code, but this before it is parsed. So in C or C++, you have some text. For example, you have a for loop, and then you can invoke some macros that change the text and make the output that you want. However, this happens at the level of text. What the macro will change text, no much different than regex, a regular expression that changes some pattern of the text. In Julia, instead, this is very different because it happens after the code has been already parsed and become the part of the abstract syntax tree. And this allows a greater expressivity because we can really, and we will see, change the expression of the macros, where each item is already it has an interpretation directly as commands and not longer just as text. So the AST is organized hierarchically as a tree of expressions where each individual element, and not only the variables but including also the operators, is called a symbol. Okay? For variables, you can use symbols to refer to the identifiers itself rather than to the object that is attached to a variable, so his value. So when you write a equal to 1, you allocate memory for an integer and you bound this object to the identifier a. With a symbol, with the symbol a, with these two dots, you will refer not to the value binded to the variable a, but directly to the variable, to the identifier itself. And expressions are objects themselves that represent an evaluated computer expression. So we will see expression themselves are even this one are object in Julia. So how can we create expressions? Well, we can do something very similar to what Julia does when it parses some code. We call the method parse, and we parse a string. Here we have an image that here you have this a equal b plus 2 as a command or written in a text. What Julia does is that it takes it as a string and it uses something similar, if not exactly this one, and it parses in an expression the text that it reads. And as I said, the type of this expression one is expr, that is an object. So even this one is an object of type expr, even expressions. There are other two ways to create expression using here these two dots and the expression under parentheses. Or using a quote block. So if I use this dump, I make a dumping of the expression, and something interesting is that I start to notice that here is already a hierarchical, a nested representation. Why is that? Because first we have an assignment. So on the top we have an assignment of what? Of a is the first argument, this is where the assignment is done. And what is assigned? Well, this is another expression, and this is the expression of a call of the plus operator that in Julia is just any other function. So we call plus with the parameter b and 1. So I can use these three using the expression constructor and make the tree more explicitly. So this is the fourth way to create expressions. And you can really see here that I'm calling first equal a, and then I'm calling another expression. So expression, as I said, is made of symbols, and to create symbol you can use the same way you did with expressions, metaparse, or using the two dots here, or you can use the symbol constructor, and you can also chain different elements to create a longer symbol, and the symbol itself is another type of object. Now I have expression. What can I do with them? Well, aside dumping and see what's happening, I can access them and evaluating them, and that's what a macro will do. So here expression 1 is this e equal b plus 1. So expression 1 argument 2 refer to the second expression, what is assigned to equal. So is this one here, is another call. And then if I take this one argument 1, I have the function that is called, that is the plus, and I have here, and you can see here that is a symbol as well. And look here, I can change this plus in a product, and when I put b equal to 2, and by the way, here, so I create this expression, b doesn't need to exist, doesn't need to be nowhere. The expression just say that there is something called b at which we add 2, and we call these things a. Whatever is b or a doesn't really matter at this point. It is only when it is an evaluated expression that will matter what really there is under the name b. So now we call it b equal 2. So we define it. If I take a, also a doesn't exist. It's not defined. Okay. Now I evaluate my expression 1, so my originally b plus 1, and the result is that now a exists because I evaluated, and the evaluation created the object, the name, created the variable a, and assigned, well, it assigned 4 because we modified the plus and we made it being a multiplication. So as you can see here, I can starting looking, it's really powerful. However, put attention because it's very powerful, but this open the possibility to have for security concerns, because of course here someone evaluate an expression can be everything you evaluate. You have full power to change the current state of the program, so it never use eval for some code that you are not sure what is doing and the origin of this code. One technical note: when you evaluate an expression, you do that at the global scope. So here in this example, I have a function foo, and I have a local variable, and I try to evaluate an expression where there is this local variable here. And here I'm calling this function. So when I call this function, it will happen the evaluation here of the expressions, and I will have an error. Why I will have an error? Because the evaluation, as I said, happens at the global scope. So like here, if it is here, but being here at the global scope level, this evaluation doesn't know nothing about this local variable that exists only within the function foo. So put attention that when you evaluate an expression within a function, you are still at the global level, so you don't have access to local variables. Okay. Sometimes you want to access the actual value of a variable rather than the variable name itself within an expression that you want to evaluate. So if you want to refer to the value of the variables, you just interpolate with the $sign. So here now it exists. Actually we created it should exist, because they give me error here, so a is equal to 4. Using this one, I'm evaluating these expressions, and if I dump it, you will see that I don't have a anymore, but I have directly 4. So here it just replaced with a with its value, and when I evaluate 4 plus 2, I think. B, I must be 2. If I have 6, it must be a 2, yeah. Otherwise it would have been strange. So now let's gonna say that a is equal to 10. As you can see here, I have no changes. Because here I don't have a. I have the value of a, that is 4. Whatever happens then to a doesn't matter. While here I have the name b. So if I change b and then I reevaluate the expression, this change because it evaluates with whatever, putting whatever is the value of b at the moment where I have evaluated the expression. And now that we quickly saw expression and symbols, let's see how can we put this one in, how can we use them in macros. So one of the best uses of macros is that they allow for package developers to provide a very flexible API to their packages. But what do I mean? I mean that using macros, you can let your users to write very concise code, and then you use the macro to expand it to what your program needs to do. And here I have an example that I think we introduced already in the kickoff meeting of the API of Jump and the API of Piomo. We can go and see this link here for how the constraints are made in Jump. And you can see here, this is the constraint for Jump. We will see this one more in details in the second lesson. But you can see here that here is how you use a macro with this hat symbol. And you can see that you just say then where you go, you give a name, and then you write your constraint in a very simple way, I would say, without many strange things to add to the constraint. Now let's compare this with Piomo. So Piomo is something very similar but for Python. And here you can see that the constraints, you have always to put model, and you have to say constraint is much more verbose the way you build your constraint here. And this is why you don't have macros here, so you cannot simplify your expression using macros. So here I have listed a few examples of packages that use macros. Actually, this one is not a package, it is in base. So here is broadcasting. So for example, when you have to broadcast all the elements of a long equations, so instead of putting the dot blah 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 every time, you can just use this macro here, and this macro here will add automatically the dot to all the operation in your equation on that expression. Or here, another very useful macro is the pipe operator. So Julia has already a pipe operator, this one here, but this package here, and change it by using placeholders so that you can use the pipe operator for functions with more than one argument. So for example, here we'll put the 10, and here the result of this one we'll put it here on the second argument, and finally put it here. So instead of having to write the whole, so here you couldn't have written this expression without a macro. You would have to change, you would have to make one function within another very ugly things, and instead with the pipe operator you can use a much more clean syntax. And here with multi-dim equations, similar, you write an equation in a very concise and nice way, and this is reformulated your expression in something that is much more ugly to read. So here is how to use a macro. Let's see now how we define a macro. Well, they are defined very similar to functions. with the keyword macro that replace the keyword function, the name that we want to give to the macros, and then the parameter. But notice here that the parameter are actually expression themselves, and this macro here will return another expression. So it takes expression as input. Here we use it to make a custom loop where we have a control expression and a working expression, what is done inside the loop, the for loop. And here is created the macro where we say for I in control expression and then do working expression. So where I define here this macro, then I can invoke the macro here. So I call custom loop and then I define between 1 to 4 and then what to do, println, and notice that here I define the I here inside the macro and I can use it in the working expression. I can use like this one, I can use many other things, I can put an if, I can use it for a very different kind of things. So it's very already pretty useful but simple but useful macro. And here with this macro expander, I expand the content of the macro, and I think that it went somewhere here. I think it's better I put it here. So here, if I want to know how this macro expand, I have here the output and how it has been indeed expanded. One last point about macro is we can have another kind of macro called the string macros, non-standard string literals, and they are invoked with this syntax here where I put XXX in front of a quote or a triple quote, double quote string, and this is used, it is a true macro, but it is used mostly to process the text inside given as an argument to the macro. So here is how I define this special kind of macros with the name and with this str that I add to the name, and then I use it here print 8 and then I put this under double quote, and you can see here, I think, yeah, that it has been this long string has been put every 4, so every 4 letters it go back on a new line, and here is the same. So maybe you don't need it like this one, but is used, for example, to mark down, or it is used, and we will see in this segment later on, these string macros are used to import and evaluate code in R or in Python. As I said, these are true macro, so I can replace this custom loop that we did earlier with a macro, with a string macro, and use it in this way with this as a string macro indeed.